let's continue what we were doing last time. I tried to do the classification of surfaces quickly at the end and then ran out of time. So yeah, I hope that by now you try to do it by yourselves at home with what we said, but I'm going to do it now. So, basically, so classification of surfaces of closed surfaces. So the theorem is that if sigma is a closed, and remember closed for manifolds means compact and no boundary. So this means compact and no boundary. And of course connected, because if it's not connected, then it's several manifolds. So closed and connected surface, that just means a two-dimensional manifold. Then sigma is either diffeomorphic to a connected sum of tori, so of G tori, I equals 1 to G, or sigma is a connected sum of RP2s, I equals 1 to K. And here, the convention is that the empty connected sum is a sphere. So, I guess you could think, or sigma is diffeomorphic to S2. But you can think of S2 as being the neutral, the zero of the connected sum. When you take connected sum with S2, we do nothing. So kind of it's a reasonable convention that the empty connected sum is S2. Okay. And then the other thing that is interesting here is that you can actually replace two RP2s with a torus. So, if K is bigger than or equal to 2, I guess, maybe this is an observation. If K is greater than or equal to 2, and then the connected sum of RP2s from I equals 1 to K, so this is equal to, so I guess you can write K as 2G plus L, where L is 0 or 1. I guess you can always do that. And then RP2 is going to be diffeomorphic to the connected sum of G tori, and then the connected sum of L RP2s. So basically you can divide K by 2, and G will be the number of tori, and then the L will be 0 or 1. But it's even true if G is less than that, and L will be bigger than that. So this is kind of always true. Of course, provided G and L are greater than or equal to 0. Actually, sorry, you need K to be strictly bigger than 2. This is not true if you just take the connected sum of two RP2s. Okay? Yeah. And this is also, if you want, this is also diffeomorphic to the connected sum of G Klein bottles with L RP2s. Okay, so basically every two RP2s together is a Klein bottle. And actually that's true for any G, for any K, even for K equals 2. Okay, actually, this is not actually very nicely written. Again, if I was doing it on a tablet, it would be easy to rewrite this. But since I'm not doing it on a tablet, I can not be lazy and still rewrite it. So let me rewrite this. So if K is bigger than or equal to 2, then we can write this with a Klein bottle. Okay, so that's true. You can always do that, even in the case k is equal to 2. 2 RP2s are already a Klein bottle. But then, if k is strictly bigger than 2, and k is equal to 2g plus L, then, of course, with L, so here with, L greater than or equal to 0, g and L greater than or equal to 0, and here 2. So k equals to 2g plus L, and g and L greater than or equal to 0. And here, you actually need L to be greater than or equal to 1. So g greater than or equal to 0, and L greater than or equal to 1. Okay, now it's the right thing. Then this guy here happens to be the same. You can replace each Klein bottle with a torus. But the point is that you can only do that if you still have an RP2 there. Because if this term here is empty, if this term here doesn't exist, then if you replace k with tori, then you get something orientable. That doesn't make sense. It's not possible. So then, this guy is also diffeomorphic to the sum of g tori with L RP2. Okay. That's the correct statement. Okay. All right, so how do we do that? So let's prove the theorem. So we're going to prove the theorem using Morse theory. So I said, last time that you can cancel all the handles. So, if you start with a Morse function, you can cancel all the critical points. Or, you can look at the handle decomposition, you can cancel all the handles. Except, basically, you can cancel all the 0 and the 2 handles except for 1. So you can always assume that your Morse function, that the handle decomposition that comes from a Morse function, and a gradient-like vector field will be of the form, so you have one unique 0 handle, you have a unique 2 handle, and then you have a bunch of 1 handles, potentially. Okay? So this is in a way already the classification, or of course it's not so easy to see what are all the possible ways to attach 1 handles so that this thing actually can be closed up. So this is kind of the content that's left of this theorem, is to analyze the complexity of attaching 1 handles in a way they can be closed up with a unique 2 handle. So that's kind of what I tried to explain last time, but we ran out of time. So let's kind of start that. So I'm gonna write it like this. So a 0 handle is a disk, and the boundary is the circle. So what is the attachment of 1 handles? You have to choose an S0, and then you have to thicken it. Okay? So you have to choose an S0, so they're just 2 points, and then you have to thicken it so that you attach the 1 handle. Okay? And then here's kind of one thing that you can see is that there is only one way to attach this handle, this 0 handle, in a way that makes this thing still orientable. So, basically, if you attach the handle, sort of in this direction, meaning that that's kind of how you thicken it. So you put the handle like this. Then that's still orientable. What you really have to do is you have to take a path that goes through the middle of the handle and comes back, and you see if that path is orientable. And that's all you need to see to check orientability. So really, basically, if you started with your disk and you attach a handle like this, in this way, then you're still orientable. So as long as you can think of, attaching a bunch of handles, just like choosing pairs of points, and in whatever way you want, whatever, a bunch of them. And each of them would be a handle attachment. But then, if you want it to be orientable, and let's do the orientable case first, then there's kind of a unique way to attach these handles that has to do with the orientation of the boundary of the disk. So basically, every time you have an arrow going this way, you have to have an arrow going the other way when you look around the disk, no matter where the S0 falls. Because basically, you can think of these handles as being kind of independent. You could think of them as attaching all at the same time. We showed last time, they don't have to attach to each other. They can just all attach directly to the 0 handle. Or in other words, like by a handle slide, you can always kind of make them go to the original 0 handle. So you don't have to worry about sort of attaching a 1 handle to a 1 handle. It's basically, I explained this in 2 different ways. I kind of explained this with the handle slide argument, but also with the argument of moving up and down critical points. Like you can actually make them all have the same critical value if you want, which means they can't attach to each other. They will attach to the 0 handle all at the same time. Okay? And then the next thing you need to see here is like, okay, so after you attach a bunch of 1 handles, if you want to finish your handle decomposition, then you have to have a circle at the end to attach a 2 handle to. Okay, otherwise, that doesn't work. Like you can't close up your manifold. So what you have to see is that these 1 handles, they have to be attached in an intertwined way. Because basically after you attach a 1 handle like this, what happens is that here you have one connected component of the boundary, and here's another connected component of the boundary. And the only way to get a circle at the end is if you actually attach a 1 handle that will kind of match, that will have an end here and an end somewhere else. That's the only way to attach a handle that will connect the 2 parts of the boundary and get back to 1 connected component, to 1 circle. So that's kind of why you have to have, they have to be intertwined. And at first, you could think, okay, they can be intertwined in a kind of a crazy way. But then you can use handle slides to kind of prove that actually they can be intertwined pairwise. So basically, it's like if you, actually this should be a different color. So I mean, say that this guy is intertwined like this with the pink one, and then this guy is intertwined like this with the red one. And let's just say I have. So I'm just going to give you an example. So let's say So what I'm trying to claim is that you can get a bunch of handles intertwined in the following way. So basically, they can be intertwined pairwise. So if this is your green handle, and this is your yellow handle, they're like this, and then you have another pair of intertwined handles. And then maybe you have another pair of intertwined handles, but they have to be, or you can always make a handle slide so that they are separated like this. Okay, so like the handle attachments, the 2 S0s, they come like this, so these handles have to come in pairs. And why is that? So I'm claiming that this is true. So why is that? So first of all, you notice that you cannot have the handle attachment, one of the handles having nothing in between. And that's because, if this is 1 handle and all the other handles are attached over here and there's nothing here, then this is a new connected component. So you will not be able to attach a 2 handle. You have to have a unique circle on the top. Okay, so is that clear? If I attach I'm first doing orientable. So I'm attaching an orientable handle. Basically, every time I attach an orientable handle, or if at least the first one, if I attach it like this with nothing else attached in between the S0, then this is going to break the number of connected components of the boundary. So here I have 1 connected component, and here I have another one. Okay? So if all my 1 handles are attached like here, all my other 1 handles are attached here, then this thing is going to have at least 2 connected components. Because this one doesn't talk to this part at all. Okay, so this is not a good situation. So I can't have handles like this. Which means that I have to have at least 1 handle connecting here. Okay, one handle, I have to have a one handle that has an attachment here and then another attachment here. Okay, and then the question is, well, is this guy the closest to this or not? Maybe, maybe I'm attaching another handle here, and then then this way I'm not intertwined like this. I have something kind of in the middle here, bothering me, right? So maybe I should use another color because green and yellow are very similar. Maybe pink. So say that I have something in the way. So I'm attaching my yellow handle like this, and I have some pink guy in the way. So then how do I deal with it? Well, what I can do is I can do a handle slide through the white guy. So that means I take my handle. I can try to draw a picture of what's happening. So you see, so sort of I have this white handle here, and I'm writing it like this. And then my pink handle is here. So what's the handle attachment that I want? So I want to take my handle, and I'm going to drag it on here like this, all the way to the other side of the handle. So one way to think about this is the following. So if this is oriented like this, then I can think, like the back, I can think of this as an arrow that enters this handle kind of facing the back. So sort of, it's like this, and then it enters this handle facing the back, like this. So it's going to come out, and the back's going to come out first. So after, it travels through this handle, it's going to come back here. So it's going to be out of the way of the yellow one. And then it's going to come back. So the back entered first, and the back is going to leave last. So it's going to be like this. Okay. And notice, it's still an orientable handle, so it's OK. And then that way, I can basically take all of the handles that are attached here. I can take them to the other side. Then I can leave my yellow guy free to be as close as it wants to the white guy. Okay? So basically what I'm saying is that if I start with any kind of crazy thing, as long as my yellow is intertwined here, then I can move the other guys back there so that my yellow ends up here, close to the white one, without anything in the middle. So this is kind of the simplest situation. So what this means is now I have this thing here, which is a closed system. And you can see that when you attach these two handles, you actually don't increase the number of connected components. So when you just attach the white guy, you do increase by one, but then the yellow guy solves the problem and brings the number of connected components down to whatever it was before. Meaning, when you enter this guy, then you go through the two handles, and then you leave here. So it's the same number of connected components. It's just going here, and then maybe here you break it into more connected components. But sort of this part here, these two one handles intertwined like this, they don't really increase the number of connected components. So and what this means really is this figure like this. So you're attaching one handle, you take one part of your boundary, you're attaching one handle like this, and then you're attaching another handle like this. So this is really what this picture represents. Okay. So this is it. Maybe, this kind of the rest of the boundary of that zero handle is already broken up into other pieces, but whatever the piece that you're attaching it to, you're going to be doing this. Okay? So this is kind of an induction to see that kind of no matter which configuration you start with, you will be able to either you have more than one connected component, or you have two intertwined ones. That if they're not perfectly intertwined, then you can kind of push all the rest like this, so that they will, after some handle slides, they're going to be perfectly intertwined with nothing in the middle. Okay? I mean, you might think, okay, what if I had a pink one in here? Then what would you do? And you can convince yourself without too much thought that then maybe you would do something and you would find always like an intertwined pair. And then you take your intertwined pair, and then you kind of do the rest with with what's left. So the conclusion is that after this procedure, these handle slides are done enough times, they always end up in a situation like this, where you have these intertwined pairs of one handles separated in the circle. Okay, so you have 2 one handles at a time. So basically what you're doing is, like when you attach the first pair, you go from, your disk and you attach the first pair. So then after that, you're attaching something like this. So this represents a pair of one handles that are attached in an intertwined way. And then the next one is another thing like this, and so on and so forth. So at the end, basically you start with your disk, and then you have a bunch of guys like this. And then you end up with a circle, which is a condition that I said I wanted, that I needed to be able to close it up with a disk. Okay? So for each pair of one handles, I basically have one torus. So, so each of these guys corresponds to one torus. And this procedure here is exactly the connected sum. So basically, if orientable, then I have to have an even number of one handles. So I have 2G one handles, and that means they come in pairs. So I'm going to have G tori. So you can think so basically at the end you have the connected sum of G tori. And I guess if you want, you can kind of take a connected sum with S2 here and a connected sum with S2 here, which correspond to the 0 handle and the 1 handle and the 2 handle. But taking a connected sum with S2 is like doing nothing. Okay? Is that clear? Is the connected sum procedure clear? I guess I didn't completely explain it, but kind of if I have these 2 surfaces, I just remove a disk from both, and I glue them. That's the connected sum. So doing that with the sphere, that doesn't change the topology. Okay, so I'm actually doing this in the smooth category even. Okay, so that's for orientable surfaces. And now if I allow my surface to be non-orientable, then I have to see what happens. In a way, it's easier because if you kind of allow, well, at least it's easier to see that you have, it's easier to see how to construct K, the non-orientable surface that comes with K RP2s. Because basically, now the non-orientable case. So if you start with your 0 handle and you want to attach a 1 handle, you choose 2 points. And basically, if you want it to be non-orientable, there's another way to attach the 1 handle that's going to mess up the orientation of the surface, which is if you glue the surface like this. Okay, so basically, if you attach your 1 handle in a non-oriented way, so this guy here, it's easy to see that if you take a path that goes from here to here and then travels along the middle, the core of this handle, that it's going to be a non-orientable path. Disorienting, I guess. But the thing that's actually good about this is that the number of connected components of the boundary is the same. So the boundary is still a circle. Because I go like this. As I follow the handle, I get to here, and then I go here, and then I follow the handle, I get to here, and then I close up. So you can also think about attaching a handle as just gluing this piece with this piece. It's like your handle, you shrink the handle to nothing. Topologically, it's the same thing. Like the handle doesn't exist. It's just a gluing. You glue this to this, and that's the handle attachment. So you can think about it that way. But anyway, what this is saying is that now you have a non-orientable surface, which is it's easy to see it's the Möbius band. And then, so basically start with your 0 handle. you attach your Möbius band, which I'm going to draw like this, kind of schematically. Sorry, this is not the Möbius band. This is this one handle, and then plus this disk, it's the Möbius band. And then what happens is if you attach a 2 handle now to close this up, that's the same thing as actually shrinking this circle to nothing. Attaching, just basically putting a disk on this thing, it's the same as kind of shrinking this path to nothing. And then this is, after, so this plus a 2 handle is an RP2. So it's the same as kind of shrinking the circle to nothing, to a point. So, then you're going to have, basically just this, where you can think of this really as an identification of this side and this side. And I already said this last time, but one way to see this is, maybe you take this point here and take a disk around this point. This point is the same. Take a disk around this point. And when you remove this disk, then what happens is, basically now, this guy is not identified with this anymore. But this is exactly a Möbius band. It's exactly this guy here. Okay? So is that clear? So basically, the simplest thing you can do is attach one non-orientable handle, and then you're going to end up with a circle that can be capped off, and you get an RP2. So this is just one RP2. Okay, so this is one RP2. But then, of course, you can keep this procedure, and you can keep them. You can keep adding one handles, and then now, when you think globally, as soon as you have one non-orientable handle, then kind of globally, it doesn't make sense to talk about orientable or non-orientable anymore, because it's already non-orientable. But you can kind of still talk about it locally, if you attach the handle in a way that's not intertwined. So, sort of if you have, if you attach a handle here, and there's no other handle attachment here, no matter what happens here, you can still talk about whether this is orientable or not. Okay? Because you can just still take a path here that doesn't interact with the rest. So say that I already have a non-orientable handle here, like this. So then I can say, well, this handle here, is this orientable or not? So then I have to kind of consider what happens if it's orientable and if it's not orientable. So basically, one thing to see, it's kind of a tree of possibilities they have to consider. But if you already have a circle up to here, if kind of this thing here is already a circle, no matter what you had before, then basically, if you want to just add orientable handles, it's the same problem as there. Okay, so kind of the situation here doesn't actually matter. It doesn't matter if you already had something non-orientable happening here or not. Basically, if you isolate one part of the circle, and you can still talk about like attaching orientable handles there, which means that kind of no matter what you have below, you can always add T2s, and then end up with an S2 at the end. Okay, so that's so basically you can always do that. And then it's also clear that, so that's one thing you can do, but it's also clear that you can also always attach sort of non-orientable handles that come by themselves, one at a time, that don't intertwine. So here is your first non-orientable handle, and then you can add another non-orientable handle, and then you can add another non-orientable handle, and so on. So each time you do that, you basically have another connected sum with RP2. So basically, like doing this, we see kind of we can see how it branches out. So you can either kind of take So basically this means that you can construct surfaces that are either connected sums of RP2s, connected sums of tori, or something mixed, like a bunch of RP2s and then a bunch of tori. Okay? So you can kind of see that this is in a way, this is not quite the classification yet, but this is at least two families of surfaces that you can construct. And then I already said, if you start only with orientable handles, then you can always reduce using handle slides to the case of just connected sums of tori. So the last thing we have to see is what happens if you start to attach intertwined handles in the presence of a non-orientable handle. So like for example, so if I start with this picture and I add one non-orientable handle, and then I attach another handle, say here, like in an intertwined way. What can I do? Like, what does this correspond to? And the point is, because I have this non-orientable handle, I can actually move this by a handle slide. I can move this in a way over here, and then it's not intertwined anymore. So basically, if I have a non-orientable handle, then it doesn't actually make sense to say to say that it's intertwined with that. I mean, it's intertwined with that particular handle attachment, with this particular S0 here. But I can move this handle slide, this guy by a handle slide away. So then I don't have to consider this anymore. Okay, so that's kind of, it's a little subtle, but that's kind of the essence of it. So if you have one non-orientable handle, then if you have a bunch of stuff in the middle, like a bunch of other handle attachments in the middle, I can use a handle slide and take them all away. So at the end, my non-orientable handle can be considered just by itself, all separated. Okay? Okay, so that's kind of the first thing. So basically, that means that that any surface can be written as basically, this is kind of the end in a way of what I said, that any surface can be written as a connected sum of RP2s and T2s. So kind of this is the conclusion here so far is that any surface is basically the connected sum of some tori with the connected sum of some RP2s. Okay. So I mean, this is already a classification if you want. Okay? Any questions so far? Yeah. No, mas aí, exatamente. This is actually an interesting question because if you put one that's non-orientable when you look at the orientation of this particular circle, when you go through the non-orientable handle, then you change the orientation with respect to the circle. So it's actually an interesting, kind of comment. Like if you start with, say, a non-orientable handle like this, and then you say, well, I want to attach a handle like this that's non-orientable with respect to the orientation of the zero handle. Then what happens is when you do a handle slide, kind of the back goes in first, so the back comes in last. No, the back goes in first, so the back comes in first. So after the handle slide, it's actually going to be like this. So this is actually an orientable handle separated. So this actually breaks up the number of connected components. So this is not enough to close up the surface. You need another one handle. So you're going to kind of go back to this argument. So I think it's cleanest, if you really want to classify the surfaces, to see that every time you have a non-orientable handle, you can take all the other attaching points from inside it. You choose one, of course, you can say this is the inside or this is the inside. But you choose one, and then you take all the other attaching guys away from it. And then basically you have this non-orientable handle sitting by itself. You could have done it here, but so with the pink guy, and then you would have flipped the orange one. But like if you fix one non-orientable handle, you can keep it non-orientable by not doing a handle slide with it. So I say, I want to keep that non-orientable handle, and you take everything from the middle with a handle slide. And then if you see another non-orientable handle, you can do that too. And it's also not so hard to see that if you have an orientable handle, you can just take a non-orientable handle with a handle slide and then take it all the way to the other side without changing anything. So basically, you can isolate and take all the non-orientable handles attached all by themselves to one side of the circle. And then on the other side, you have the orientable handles. But they have to be intertwined because of what I already explained. So what this is saying is that, basically, every time you attach an non-orientable handle by itself, you're doing a connected sum with an RP2. So you do all those first, and then you look at the other side, the orientable side, and they come in pairs. So every time you're doing a connected sum with a T2. So that's why, basically the classification of surfaces here is kind of done, or is already done. Basically, every surface has to be a connected sum of RP2s, connected sum with a connected sum of T2s. Okay? I mean, I can write down the details, but I think it's kind of, I've already said everything. But there's one more thing that I'm missing. It's not really in the classification of surfaces, but it's kind of in the understanding of the classification. I said, basically, as long as it's non-orientable, I basically don't need any of the tori. I can just have RP2s. And that's basically, you can see this just using handle slides. So I guess the last thing that I kind of want to prove using handle slides is that if you do an RP2 plus an RP2 plus an RP2, that this is diffeomorphic to a T2 connected sum with an RP2. And actually the first part that I wrote down, which is that this guy, 2 RP2s is a Klein bottle, is pretty much trivial. So that there's really nothing to prove. That every time you have 2 RP2s, you can substitute that by a Klein bottle. That's just saying that when you glue 2 RP2s along the boundary, you have a Klein bottle. Okay, that, I guess I won't prove that. That's an exercise. So I guess, a very kind of simple exercise is that, and you don't even need Morse function for that, Morse theory for that. Just that, if you glue 2 RP2s, that's a Klein bottle. But, the thing that the claim that I want to prove is this one. This one is not trivial. And this one you can, basically prove with handle slides. So how do we prove that? So we look at the diagram that you need, the handle attachment diagram for 3 RP2s, and you show that it's equivalent to the handle attachment for this guy. So what is the 3 RP2s? So the exercise is this. So let's prove the claim. So 3 RP2s would be, I have 3 non-orientable handles by themselves, not attached, not talking to, not intertwined. So say I have this. Then I have this. And then I have this. Okay. So now I'm going to use, some handle slides to make the thing interesting. So what I want to show is that I can actually perform some handle slides so that I will end up with just one non-orientable handle, and then the equivalent thing for T2, which is 2 orientable handles that are intertwined, like this. Okay? So how do I do that? So I guess, it's easiest to just think that you can actually flip the orientation of this attaching handle by going through halfway through by going through by doing one handle slide with a non-orientable handle. So the first thing maybe you want to do is you take your green guy, this first attachment guy that's closest to the orange, and you go through the orange handle once. Okay, so you go in through here, and you're going to come out here. So the first handle slide, so I guess this is a handle slide, you're going to end up with, so your orange is going to stay the same. I mean, of course, I'm kind of doing obvious isotopies. And then the green one is going to be flipped like this. This one is going to go through, and it's going to come out like this. Okay, so like the back goes in first, so the back comes out last. So it goes in through here and comes out through there. I think you can visualize the handle slide. And then the blue guy stays the same. Okay, so now what I can do is I can do a handle slide, use the blue, take the blue guy through the orange one again. So now I do a handle slide where I take this attachment of this guy over here. Okay, so that means this attaching part here is going to go through the orange non-orientable handle, and it's going to come out over here. Okay, so then the next step, so we have to be careful. So the green guy is here. The orange guy hasn't really moved. I mean, I'm just going to give a little room. And then the blue guy, this blue guy is going to come here, but the front enters first, so the front comes out last, so it actually comes out like this. Okay, and then I still have my green guy here, and my blue guy here. Okay. Okay, so now I'm almost done. So now what I'm going to do is I actually will slide this handle here through the blue guy. But now the blue guy is orientable with regards to the surface, which means, basically you can see if you go in with the back of the blue guy, with the back of the orange guy through the blue, then it's going to come out, the back's going to come out first, so it's actually going to have the same orientation in the circle. So when I do this last handle slide, so I'm going to take this guy and I'm going to slide it through the blue. Hold on. No, that's not what I want to do. Wait. Here? Oh, yeah. Sorry, you're right. This is an RP2, and this is the Klein bottle. Yeah, I guess you have to see this as a Klein bottle. So, yeah, sorry, maybe this is already kind of, maybe there's an easier way to get to where I want, which is you can, oh, yeah, okay, sorry, yeah, thank you. You can actually take this guy and slide it from here to here, and then you flip it. Yeah, so you take the orange guy, and you take a handle slide through this green guy. So you go from here to here. So what it does is it flips this arrow. Okay, so, yeah, okay, this is maybe with fewer steps. So you leave the blue alone. And then now you take this guy through here, and then you flip it. You flip the direction. So then you have your green. So basically the front enters here. So the front enters here and comes out here. So no, that's not true. Maybe it's not so easy to see with the handle slide. Maybe to see with handle slide, you have to do more handle slides. But you can see this is actually a Klein bottle, kind of independently. I think what you need to do is sim. Como é que é? Para cá? Não, o problema é que se você faz o handle slide para cá, ele vai continuar com a mesma orientação. Entendeu? I'm thinking about what's the best. I think, if you want to see this as a, I don't think you can do that without using the blue guy. Because otherwise the Klein bottle would be diffeomorphic to the torus, which it's not. So this is actually not enough. So this, over here, you just see a Klein bottle. You have to interact with the blue. So yeah, you were trying to do a shortcut, but you can't do the shortcut. You have to interact, the three handles have to interact. Otherwise, you would have this, which is not true. So far, actually what this handle slide did is you turned the, basically two RP2s into a Klein bottle. So you do need to interact with the blue. Okay, so let me go back to where I was. Okay, so precisa interagir com o azul. You cannot just leave one of them away. They all have to interact. Okay, where was I? I was taking the blue guy around. So the blue guy comes in here, and then it goes over here. So let's do that. So, I mean, this could be an exercise, but I guess it's fun. It's the last class. So it goes in here, and it comes out here. So my orange guy goes first, and then I have my blue that switches the orientation. So it goes like this. So it leaves like this. And then the green one, and then the orange one. Okay, so great. Okay, so now I see how to finish. So now what you do is you do one more handle slide, which is you take the green over here, and then you slide it over to this side. Okay, you take this green, and you slide it over to this side. So it's going to enter here, and it's going to come out here. Okay? So then it's done. So then this blue, this green enters here, and it comes out here. So that means, I'm going to leave everything else, stopped. So I have this orange handle, this orange thing, and then the green one, and the blue one. And then now, this blue one, now this green one is going to be next to the blue one, and it's going to be like this. And then I have the orange one, and then I have, wait. Oh, no, hold on. Yeah, no, the green one went here, then the orange one, and then the blue one. And then, yeah, that's right. Maybe I'm doing one handle slide too many. But then now what I do to finish off is I take the blue guy and I do two handle slides over the orange one. So, I can basically go from here to here. And no, I think that's not going to solve the problem. Hold on. Why am I getting confused? Huh? This is an exercise. It's hard to do it when you're so close to the blackboard. Did I make a mistake? This blue guy. Hold on. So here I went from here to here. Yeah, that's right. And then green one. This one? This one. Where do you want me to take it? Here? To the orange. Then I'm going to get it over here. There's something wrong. Oi. Esse aqui? Não, eu estou fazendo um hand slide com azul, né? Então ele entra e sai com a mesma orientação. O verde continua com a mesma orientação, né? Eu acho que eu preciso... Oh, no, I know. Okay, I see. So if you take this orange through this green guy, then we're done. Okay, so you take this part here, and then over here, you do the slide from this guy to this guy. And then you're done. Okay, so you really need one more handle slide. Okay, sorry this is a little slow, but when you take this guy over through this green here, it's going to leave here, and it's still going to have the same orientation. So basically, you're going to have your orange guy here, and then the rest is exactly what you wanted. So you have two intertwined orientable handles. So there we go. So this is exactly what we wanted. So this guy here is an RP2. And then this is a torus. So there we go. Okay. Maybe this is not the minimal number of handle slides. I don't know. Maybe you can do it with fewer handle slides, but this worked. Okay, so that's the end. I mean, the classification really ends here. I guess this is just to see that this is you're overcounting here. You don't need G and K. Basically, if you have as long as you have one RP2, all the other tori can be converted to RP2s. Okay? So either for non-orientable surfaces, you have a connected sum of RP2s, and for orientable surfaces, you have a connected sum of tori. And that's it. Okay. Any questions? Okay, so we're done with 2 dimensions. And as I said last time, I'm not going to worry about non-compact surfaces, because a lot of weird things can happen. You can have an infinite number of handles, and they can go in different ways. And so I'm not going to. Open manifolds are a lot harder. So let's go to 3 dimensions. So now we're going to talk about what's called Hager diagrams, which is a way to, not really classify, not in a nice list, but to understand the complexity of 3 manifolds. So now let's talk about Hager diagrams. So the idea is we're actually gonna, we're gonna pick a three-manifold, which is orientable or oriented, closed, and connected. So we're really gonna worry about only the oriented case, because the non-orientable case it's more complicated. But basically, let's just keep the orientability for now. For this class. So let's see kind of how we can recover our three-manifold from handle decomposition. Let's see how we can we know that we can build all manifolds with handles, but we can kind of see what the complexity is of this procedure, at least in a specific dimension. So that's what we're going to do in dimension 3. So because we have a three-manifold and it's connected, you can always start with a unique zero handle. So, or unique zero critical point. So let me draw schematically. So this is my three-manifold. So you have a Morse function with a unique, unique maximum. So this is a unique index 3 critical point, which is going to be the maximum. And you have a unique index 0 critical point, which is the minimum. And then we can actually, as I explained last time, we can reorder the critical points in a way so that all the index 2 critical points are above and all the index 1 critical points are below. And we can actually do what's called the self-indexing Morse function. This is just kind of for fun, but for fun, you can actually make all the index 1 critical points have value 1. And all the index 2 have value 2. It doesn't really matter, of course, what the specific value is, but what I want is I want all of the index 1 to be below all the index 2 ones, like in terms of the function f. Okay? And of course, you can say this is 3 and this is 0. Doesn't matter. You can always move it so like this. So this is called a self-indexing Morse function. The Morse index is the value of the function. It's kind of fun. Okay. So we have this, and we don't know how many index 1 and index 2 critical points there are. But there are a variety of ways to see this. But you can actually prove that the number of index 1 critical points has to be the same as the number of index 2 critical points. And why is that? Well, there are a few different ways to see this. But it's basically because the Euler characteristic of an oriented closed three-manifold has to be 0. So this is kind of a well-known fact. But the Euler characteristic of x has to be 0. And by, for example, the Poincare-Hopf theorem, this is one way to see it, this is equal to the number of critical points with alternating signs. So, this is the number of the sum of -1 to the I times the number of critical points of index I. So this is going to be 1 minus 1, which is 0. And then you have the number of index 1 critical points, and then minus the number of index 2 critical points, actually with an opposite sign. So this will mean that the number of index 1 critical points is equal to the number of index 2 critical points. This is the simplest way to see that they have to be equal. But there are other ways, like if you think about handle attachments and kind of the topology of what's happening every time you attach a handle, there's another way to see this. Okay. So let's see what's happening with the handle attachments. So, you start with your index 0 with your index 0 handle, or with your 0 handle, which is just what? A ball. Right? So you start with your 3 ball. So this is your V3. And then you want to attach 1 handle. So that means, you pick points. You pick 2 points. And then you have to attach, basically you have to thicken it up. And it's not hard to see there's a unique framing when you have an orientation fixed. And then you just glue it like this. Okay. So if you allow for non-orientable things, then you have to take into account that, you could also attach this in a non-orientable way. And then the boundary would be like a Klein bottle instead of a torus. But we're only doing orientable things now. So there's only one way. When you choose 2 points, there's only one way up to the diffeomorphism to attach a handle. And then you attach another handle, and as usual, we want to attach them separately. So basically, after you attach G handles, and I already said this earlier in another class, but after attaching G1 handles, we obtain what's called the G handle body, which is a figure, or which is a 3-manifold with boundary that's basically something like this. So the interior, the whole thing. So this is called the G handle body, and I'm going to call NG, which you can think of as really an embedded manifold with boundary inside of R3. So this, you can think of this NG as really being like embedded into R3. And this is a compact manifold, a compact 3-manifold, and the boundary of this NG is really the genus G surface with its usual orientation and everything. And the usual orientation just comes from being the boundary of this NG. That's how we usually think of the orientation on the genus G surface. We think of it as the boundary of some compact thing of dimension higher, and then we usually orient it as the boundary of that. Okay? Anyway, the orientation is kind of obvious from the embedding into R3. Okay? Not obvious, but induced from the embedding into R3. Okay. So this is what we have after you attach all the 1 handles. So you stop here. So it's kind of easy to see that when you take the pre-image of something here, really what you get is this boundary. So you can think of it like this. So you have your sigma G right here. And what's below here is your NG. And now what you have to do is you have to attach the 2 handles. Okay, so basically now you have to attach the 2 handles to this handle body here. So what's an attachment of a 2 handle? Remember, to attach a 2 handle, what you have to do is you have to choose a circle, and then you have to thicken the circle. So a 2 handle here, in dimension 3, I kind of explained this last time, or maybe two classes ago, I can't remember. What's a 2 handle? A 2 handle is a D2 times D1 attached along an S1 times D1. So that means, the boundary, what you have to find a circle in there, and then you thicken the circle, and then you glue in this D2 times D1 there. Okay? So then you glue in, sort of this D2 times D1. Okay, that's what you get. Okay, so you kind of put this over there. So basically, in other words, you choose a circle, and that circle is going to be contractible after you attach the handle. Okay? So basically, now if I have this G handle body, I have to attach G two handles. So I have to choose G circles on my surface. So, I have to, basically, I have to find or choose an embedding of G circles into my genus G handle body. Okay, so I have to choose G, G disjoint circles inside my handle body to attach. Okay, and I want to choose them disjoint because I basically, if I choose an appropriate, an appropriate gradient-like vector field, then they don't intersect. The two handles can't intersect. They're descending manifolds of different critical points. So really, you can't choose intersecting circles for this procedure. They have to be non-intersecting. Okay? So, for example, if you had just a, let's start with the easiest case, which is if I have, if my G is equal to 1, that means I just have one handle. So basically my handle body is a solid torus. So now I have to choose a circle on the solid torus. And there are lots of circles. There's for every PQ, for every P over Q rational, you can find a circle that kind of rotates P times in one direction and Q times in the other direction. Okay. But you can choose kind of the simplest ones, which are, you can think about, so there's this one, or there is, actually let me use blue. That's the usual color. Or there's this one. This is kind of, the case 1, 0, and 0, 1. But then you can actually have, circles that are wrapping in a more interesting way around the torus. And each one of them, you just stick in them, and then you can actually attach a two handle. And, kind of a proposition, which I'm not going to prove, but is that basically if you choose these in a nice enough way, after you attach these G two handles, then you actually get back to a sphere. So if these guys are chosen in a sufficiently nice way, then after you attach the same number of two handles that you had of one handles, then you end up with a two sphere that can be capped off by a ball. Okay? So I guess, it's kind of a one-to-one thing. Like if you, well, let me not write down the proposition. Let me just say this with words. So if you already have a Morse function and you look at the way that you can glue these guys together, of course, up here you have an S2. So what's the condition that you get on the circles on the sphere? So the condition is the following thing. So basically you need these circles, when you look in the homology of the sphere, to be linearly independent. So I guess maybe let me write proposition. So when you look at the image of these circles, so so you have the G circles corresponding to the G two handles, to the attaching spheres, of the two handles. Actually, it's not G circles, it's G circles. G is the number of circles. So you have the circles, I guess I can say this, the circles corresponding to the attaching spheres of the two handles are disjoint and linearly independent on the first homology of this guy. If you don't know what the first homology is, this is just the abelianization of the fundamental group. So the fundamental group of sigma G, it has two G generators. But it has a funny relation. So this is the same as Z to the 2G. So the condition that you need is that these circles are So I guess the proposition can be if your circles do come from a handle attachment, then they have to be disjoint, and they have to be linearly independent here. But this condition is actually equivalent to when after you attach all these two handles, you actually end up with a disk. And this is actually also equivalent to if you take your genus G surface and you remove all these circles, then you actually get an open disk. So this is maybe this is kind of the condition that's more interesting. Then if and only if sigma G minus the union of these S1s is homeomorphic, or homeomorphic to a disk, an open disk. I mean, if the genus is 1, it's kind of pretty clear that if you take your torus and you cut it open along any circle that's non-trivial in homology, that you get a disk. Maybe not, it's not completely obvious, but it's true. Okay? But it's true in higher dimensions too. And this condition here basically just means that after you attach these two handles, maybe now it's easier to see that after you attach the two handles, then you really get a sphere, an S2, which you can cap with a ball. So anyway, so now we basically have an understanding of how to build three manifolds. So all you need to do is look at a genus G surface and choose G circles on it that are disjoint and generate or are linearly independent in homology. So you can't choose kind of multiples of the same or, kind of, it's not so easy to actually draw disjoint circles that are linearly dependent. You can do if the genus is sufficiently big, but it's a little hard. So kind of that's how you build three manifolds. So a Hager diagram. So what is a Hager diagram? It's basically just a diagram of this. So a Hager diagram is basically, a choice of a surface, and then usually people do the following thing. They have an alpha and a beta, and alpha are G circles, and beta is also a collection of G circles. So these are all circles, so alpha I and beta I are circles in the surface. And you usually think of the alphas as the circles. These are the what is it called? Belt spheres. These are the belt spheres of the one handles, and these are the attaching spheres of the two handles. So these are the belt spheres of the one handles, and these are the attaching spheres of the two handles. So now, according to the description that I gave before, these belt spheres are just, kind of these guys here. So, basically, it's a circle, kind of, you can think of you start with your zero handle here, and then you attach a handle like this. So this is the belt sphere. It's kind of the sphere that, when you have your one handle, the belt sphere is this guy here. Or you can think of it as like the circle on the surface that's actually contractible on that one handle. So it's a circle that becomes contractible, that's contractible in that one handle. That's the belt circle. The belt sphere, the belt sphere, which happens to be a circle because of dimensions. Okay, but when you just draw this when you draw your G handle body as embedded in R3, you already have your belt circles kind of chosen for you here. So that's why I kind of didn't emphasize these belt circles. Like what really I emphasized were the attaching spheres of the two handles, which are these other these ways that you can attach. I don't know. It could be like this, and then it could be like this, and then I don't know. It could be like this. I don't know. So this is an example. So these would be the betas: beta 1, beta 2, beta 3, and beta 4. Okay, and so in a way, what this description is giving you is the following thing. So you can think of your Morse function like this, and you have your index 2 and your index 1 critical points, and then your surface it's right here. So it's the pre-image of something in between 1 and 2. And the alpha circles are basically they are the ascending manifold, or the stable manifold of the index 1 critical points, the intersection with the surface. And the beta circles are the descending, are the intersection of the unstable manifolds of the index 2 critical points. So another way to say this is kind of what I was saying. You take your surface and you choose G circles to be contractible, like in the bottom. So those are like the alpha curves. And then you choose G circles to be contractible on top. And those are the beta circles. Okay? So, and you need that condition here for the alphas and for the betas. So you need the alphas to satisfy this condition, and you need the betas to satisfy this condition. And you see that it's kind of symmetric, because it is symmetric because sort of if you take your Morse function and you just put a minus sign on it, basically it's the same as flipping your manifold upside down. So you switch the one handles with the two handles. So there's really like a symmetry between one handles and two handles. Even though you usually think of one handles as like one handle attaches along an S0, a two handle attaches along an S1, but that's because we're building manifolds from the bottom up. So then it's not symmetric. But if you just really think of handles as they are, like a one handle and a two handle are the same if you flip them, if you flip the direction of F, which means you're flipping the belt sphere and the attaching sphere. So yeah, the kind of the belt sphere, the attaching sphere of a one handle is an S0, but the belt sphere is an S1. And the same thing, the opposite thing for a two sphere, the attaching circle of a two sphere is an S0, but the belt sphere is the attaching sphere of a two handle is a S1, but the belt sphere is an S0. Okay, so when you flip it, you kind of flip attaching and belt spheres, and you flip one handles and zero handles. So that's why you can kind of think about they're kind of symmetric in this sense. Okay, so this is what's called the Hager diagram. So I mean, usually people just think about a Hager diagram as a surface, a genus G surface, with G alpha curves and G beta curves. Okay, which correspond to kind of the one handles kind of attaching from the bottom, and the two handles attaching from the top. And another thing that's related to this is what's called the Hager decomposition, which is kind of very similar to a Hager diagram. So a Hager decomposition is kind of the following. So if you think about your Morse function, also, again, self-indexing Morse function, and then you look at this slice here. So this slice here, as I explained, this is going to be your genus G surface. And I explained that this guy here is a handle body, a genus G handle body. But if you look at this kind of upside down, the top here is also a genus G handle body. So a Hager decomposition is basically, you can write any three manifold that's compact, that's closed and oriented and connected as the union of two handle bodies that are attached along a diffeomorphism of a surface. So they're attached along what? Along phi. So phi, what is phi? Phi is a orientation reversing diffeomorphism of a surface. So this is an orientation reversing diffeo. So in a way, this is kind of a simpler description of a three-manifold. So, it's kind of, in a way, you can even think about this as a classification of three manifolds. But all you have to do is understand diffeomorphisms of surfaces that reverse the orientation. But that's actually pretty hard. But, it's pretty hard to classify these guys. But, up to here, it's just a number. So you just choose a number like the classification of orientable surfaces. But then you have to choose, an orientation reversing diffeomorphism. And that can be quite hard. Porque a orientação dele vindo de baixo é uma e vindo de cima é outra. Right, so you kind of, you know this diffeomorphism by like an intricate argument. So, basically, when you think of NG as embedded into R3, so there's kind of an intricate diffeomorphism from this, what belongs to the manifold, to this embedded guy into R3. Yeah, so basically you want to find the diffeomorphism that takes the boundary of this guy seen here with the boundary of this guy seen here, and that actually is reversing the orientation of this surface. Mm-hmm. Okay. Yeah. Okay, now let's go to 4 dimensions. So let's talk about Kirby diagrams. Oi. Como? Eu acho que não tem nenhuma forma muito concreta, não. Eu acho que começa a ficar bem complicado. Se G é igual a 1, sim. So this is actually an exercise that if G equals 1, then you obtain all the lens spaces. So, so if G equals 1, then just actually... So if G equals 1, then actually, if you just have to pick one curve on NG. I mean, you can always pick the alpha to be sort of your standard. You can always pick the alpha to be this guy. Like when you choose this NG to be the standard thing, that means the alpha is this standard, contractible curve inside of the solid torus. And then the kind of what happens to the beta is the beta can be the guy that's representing the class. So the beta can be, the class PQ inside of Z2, which is the homology of the torus. Which means, this is the curve that rotates P times, basically you take in R2, you take the vector PQ inside of R2 mod Z2. So that's going to be a curve on the torus. So if this is your torus, that's going to be a curve that rotates P times in one direction and Q times in the other direction. And it's an exercise to see that this is a Hager diagram for this. So this is a Hager diagram for the lens space LPQ. So this is a lens space. it's just the quotient of S3 by some action, of ZP. You probably know what this means, right? Okay, no, okay. Okay, I'll define this later, maybe after the class. If you don't know what it means, it's okay. But I want to talk about two more things, which are Kirby diagrams quickly and the Poincare conjecture. So well, I can quickly define this. This is just the following thing. So this is S3 modulo some quotient, and the quotient is the following thing. So if you have Z1, Z2 in S3, which you think of it as inside of C2, then you say Z1, you define an action the following way. So K times Z1, Z2 is e to the 2 pi I k over p, and then e to the Z1, and then e to the 2 pi I k q over pz2. I think this is what it is. And then, so this is an action of ZP. So you take this. So this is an action for K in Z mod P. This is an action of ZP in S3, but it also depends on a Q. And if Q and P are independent over Z, so if they're rationally independent, then this action is going to be free, and then you can divide this by this action. You can take the orbit set. This will be a manifold, and that's called LPQ. Okay. All right, so now let's talk about Kirby diagrams. So this is a way to understand, again, it's not a complete classification, but it's a way to understand four manifolds. So I just kind of want to quickly tell you what it is. And what I find fascinating about this Hager decomposition in the Kirby diagrams is that to study 3- and 4-dimensional manifolds, we can't quite see them because they don't embed into R3, which is the world we live in. But because they're low enough dimensions, you can almost see them, or you can represent them kind of very concretely. Like with the Hager diagrams, you see it's very concrete. With Kirby diagrams, it's slightly less concrete, but it's still concrete. So, how do you build a four-manifold? So again, we have a four-manifold which is closed and oriented, and of course connected. Otherwise, it would be more than one manifold. So again, you can you take your Morse function. You can assume that you have a unique zero critical point. So I have a zero handle, and I have a unique 4 handle. And then the complexity, of course, lies in here. So you have 1 handles, 2 handles, and 3 handles. So let's see how we can describe these things. So your unique one, what is a unique zero handle? So your unique zero handle is a B4. It's a 4-dimensional ball, which of course I can't draw, but I know what it is. So now the question is, how do we glue the 1 handles? So how do we glue a 1 handle? We have to choose. We have to look at the boundary of the 4 ball, which is a sphere, which is an S3. So when you look at your S3, well, S3 apart from a point is just R3. So you can think of your S3 as just R3. So really, what you want to do is you want to look inside of R3 and you see how you can attach these things. So you look inside of R3 and you see, well, how can I attach 1 handles? So I have to choose, how do I attach a 1 handle there? I have to choose an S0, so I choose an S0 inside of R3. I have to thicken it up. So I thicken it up like this. So I have two balls. And then I have to attach a one handle. So that actually means, I can think of it as actually just removing the two balls and gluing the two surfaces. So, I can have my, what would be my one handle? My one handle is just an S3 times, it's a B3 times I, a B1. But I attach like this. So that means I actually remove these two, and I have this one handle connecting the two that doesn't fit in my R3. But as I explained in the case of surfaces, you can also do this for three manifolds. I didn't say that. But you can just kind of suppress this direction and just think of it as I remove these two balls and I glue them. Okay, so basically you can think of attaching a one handle as you take your R3 and you take two spheres, you remove them, and you glue the boundaries. So you basically, after you attach this one handle, what's the boundary? The boundary is going to be this S3 with some funny operation. And the operation is, when you come here, this point is identified with this point. Actually, it has to be, basically it's like this. If it's oriented, it's a reflection here. You can think of it as, it has to be a orientation reversing map. Because if you enter here, you have to come out this way. Okay, so basically you can think of identifying these two with some kind of reflection map here. Okay, so you have to attach a bunch of one handles. So that means you have to choose several pairs of spheres of R3 to remove and to identify this way. So after attaching a bunch of one handles, and actually you can, up to an isotopy, you can actually line them up. This is how Kirby did his diagrams. So he lined them up, and guess you identify them. I'm going to draw the spheres with different colors. So this sphere, and then you have this sphere, and then so on and so forth. So this, is the picture of what you have after you attach all the one handles. So you're going to have a bunch of pairs of spheres that you can kind of line them up inside of R3 like this. Okay, and now you have to attach the two handles. Okay, so how do you attach two handles? Well, remember you have to choose a circle, and then you have to thicken the circle. Right? So you have to choose, a circle. You can choose, a circle like this. And then you have to thicken the circle to attach your two handle. So what is the thickening of a circle inside of R3? So I'm not on a surface anymore. I'm inside of R3. So I have to thicken the circle. So I have to look at an embedding of S1 times D2 inside of R3. Or not R3, inside of this kind of surgered R3, which is actually really what we have. So inside of this, Well, let me not write this down. I don't want to give it a name. But this thing that I have after I did the identification of spheres, I have this new three manifold, which is the boundary of what I have of my four manifold up to the one handles. Now, to attach the two handles, I have to choose a bunch of circles. And choosing a thickening of the circle is the same as choosing a framing of the knot. So I have a knot, and then I think of it as being framed. So that means, I have a normal vector field that's, defined along the knot. But actually, I can think of a framing as actually as a braid. It's like another knot like this. So I have to choose a bunch of circles. But of course, the circles can actually they can touch the one handles. I can't assume that they don't touch. So maybe, I have another knot like this. So, this, is kind of touching the one handle. And then I have to have a framing. I don't know, I'm doing something pretty intricate. And then, I can do something kind of more trivial. I can, take a knot that goes here and like this. Why not? I don't know. You see kind of you have a lot of freedom. So anyway, I think I might have to. Yeah. So this is it. Actually, this is what's called a Kirby diagram. So this is the diagram that represents what you do after you attach the one and the two handles. So this is the Kirby diagram is the representation of this. This is the Kirby diagram. And then now you're like, okay, now I have to attach three handles. How do you attach three handles? Well, you have to choose these two spheres in there that you have to thicken. So it's a little bit more complicated to see. But now there's a theorem that says that once you specify this thing, there always exists a way to attach three handles and four handles to get a closed-oriented manifold. And this way is kind of unique. I mean, it's unique in the sense that there's only one manifold that you can construct. So I mean, you can always do things like, stabilizations and like things that cancel out. But up to like kind of, if you just want to, up to basically having, up to the manifold that you obtain, there's a unique way to do this. So there are more than one non-equivalent ways, but you obtain the same manifold. So I guess it's already not obvious that there exists a way. But it's true. Like once you have a diagram like this, there exists a way to attach three handles so that at the end, you just kind of you get back to your S3 that you can glue up, that you can close up with a B4. But not only that, there's a unique manifold that you obtain with this procedure. So that implies that this Kirby diagram is sufficient to describe a four manifold. So that's what a Kirby diagram is. And then there's something called Kirby calculus. So like Kirby kind of figured out what happens with these handles, and when you do handle slides, and when you have like a trivial pair that cancels out. So there's a whole beautiful thing called Kirby calculus, which is like what happens to these knots and these braids as you do handle slides, and things, kind of very interesting things kind of happen. And some people actually do that by hand, where they're trying to tell if two four manifolds are the same. They look at the Kirby diagrams, and they see if they can find Kirby moves that go from one to the other. So that's low-dimensional topology. So anyway, that's Kirby diagram. Any questions about this? OK, so to finish, let me say a little bit about the Poincaré conjecture. So the Poincaré conjecture well, Poincaré, I think it was in the beginning of the 20th century, like 1903 or 4. He was kind of inventing homology theory. Of course, he didn't have the tools that we have to understand. He was doing it probably like with triangulations and things like that, simplicial homology. But anyway, he kind of came up with homology theory. And he said, well, if there's a manifold, a three-manifold that has these homology groups, then it has to be a sphere. So that he kind of wrote a paper like that. And then I think 1 or 2 years later, he was like, actually, never mind. That's wrong. And he kind of came up with, he realized that there were these things called homology spheres, which are manifolds that have the same homology groups as the sphere, but they're not homeomorphic or even homotopy equivalent to a sphere. And then he was like, well, but actually, then he discovered kind of the fundamental group after that. And he realized it's different from homology. And he's like, actually, there's this kind of stronger invariant, which is pi1, which is stronger than the first homology group. And that one, he computed that it was not zero. It was not trivial for these other manifolds that he had constructed. But then he still didn't manage to prove what he wanted, so he kind of stated that a conjecture. So what Poincaré stated was that if you have a three-manifold which is closed and connected, if pi1 is 0, then Y is a sphere. So, he stated that, and believe it or not, it was only proven that to be true in 2007. So this was proven by Perlman in 2007 with very advanced techniques, like very advanced Riemannian geometry techniques, like the Ricci flow. So, have you use kind of infinite dimensional spaces, and you look at flows of these things where you vary the metric. But anyway, it's a really long story. 3? Oh, maybe it was published in 2007.
The papers were never published.
Okay. Yeah, anyway, I don't remember the year, but yeah, okay. In 2000 somewhere. But as with many things, like the original paper is really badly written, and it takes a few years for the experts to understand the proof and to actually say, okay, this is correct. And maybe he was offered the Fields Medal. I don't know. Anyway, I don't know the history so well, but anyway, it took a long time. This was 1900 something, very early, about 100 years. But in the meantime, when you can't solve a problem, what you can do is you can change the problem. So, you can say, well, I don't know how to do this in 3 dimensions, but, what can I say in other dimensions? So I guess, in 2 dimensions and in 1 dimension, this is kind of obvious by the classification. So, so you can ask the generalized question, generalized Poincare conjecture, which is if I take a manifold of dimension n, and say I assume that pi1 is 0, what can I conclude? So is x1 a sphere of that dimension? First of all, when you start playing with these things, you see that you have to really say what relation you want to the sphere. So, anyway, for like n equals 1 and 2, it's pretty much diffeomorphic. This is true. So for n1 and 2, this is a theorem. And it's basically because of the classification of curves and surfaces. So we know that a one-dimensional manifold is closed. It has to be a circle. That's kind of the only thing. Or like a union of circles. So that's kind of the end. And if you're a sphere, if you're in dimension 2, then if it's closed, then you have to be one of those things that we classified today. But if the first fundamental group is 0, in particular it has to be oriented. And it has to be a sphere. Because any higher genus thing has non-trivial fundamental group. So that's kind of obvious, so it's diffeomorphic. But in higher dimensions, the question is not so subtle. And in fact, you see for 3 manifolds, it took a long time. But Friedman proved, actually, in higher dimensions, so if n is greater than or equal to 5, it's actually proven, and this is due to Smale, we can prove that the generalized Poincare conjecture holds for a homeomorphism. So if n, so that means, if your manifold is simply connected, then X is homeomorphic to a sphere. Okay? And in dimension 4, Friedman proved that that's true as well. So also true. And I should say that these 2 results are both, they both resulted in Fields medals. So they're both revolutionary. But I mean, this one is a lot harder to explain. This one is relatively simple to explain. I mean, if you read Milner's book, it's pretty much n plus what I can say today. it's pretty much the proof. So this one is a lot easier to understand. And then Friedman came later and explained how to do very fancy things in dimension 4. Okay, so what I'd like to do now is I'd like to explain this theorem in about 10 minutes. So the first part of this theorem is a part that is not very hard, but we don't quite have enough tools to do, which is to prove that if pi1 of x is trivial, then x is homotopy equivalent to S3. So homotopy equivalent. That means that there's a map. So this means that there's a map from x to S3 and a map from S3 to x such that the composition of both are homotopic to the identity. That's what it means. So to prove this, you need a little bit of algebraic topology. And I don't have time to explain this now, but kind of using some not so hard theorems of algebraic topology can prove this. Basically using a mix of the Poincare duality and for those of you who know this, Poincare duality and the Hurewicz theorem and the Whitehead theorem. I think that's probably enough. And so a basic homotopy theory, you can prove this fact. So this part is, I guess I should say, not very hard, not so hard. But we don't quite have the tools right now. But the part that's harder, we still don't have all the tools, but I guess it's the part that I want to explain. Is once you know that it's homotopy equivalent, and this part actually is true in any dimension, by the way. So you can, if you're simply connected, then you're homotopy equivalent to a sphere. So that's true in every dimension. So the part that's really harder is showing that if you're homotopy equivalent, then you're homeomorphic. Okay? So basically, now it's showing that this, and it's not 3, it's n. Sorry, this is wrong. This is really wrong. Okay, so the generalized Poincare conjecture is not that. Okay, sorry, I'm getting a little confused with 3 dimensions and n dimensions. This is not true. What is true is that if x is homotopy equivalent to the sphere, then it is homeomorphic to a sphere. And what I wanted to say is that in 3 dimensions, there is this intermediate step. Okay. Sorry, I got a little confused here. Yeah. So I guess what I wanted to say is it's this. So let me take this back. So what I wanted to say is, if you try to prove the Poincare conjecture in dimension 3, the original Poincare conjecture, you basically are led to say if pi1 of y is 0, if your manifold is simply connected, then it implies that it has to be homotopy equivalent to the 3 sphere. Okay? And then the question is whether homotopy equivalent will really imply diffeomorphic or homeomorphic or whatsoever. And that's really the hard part. But actually, pi1 being 0 is not sufficient to say it's homotopy equivalent to Sn in general. So anyway, but then you can say actually having the homotopy type of Sn really is really the condition, the hypothesis that you want. So if you assume that your manifold is homotopy equivalent to Sn, so it kind of, you just see the Sn through these very rough algebraic topology glasses, then it's actually diffeomorphic or homeomorphic to Sn. That's really the question. And it's true for homeomorphisms in dimension 4 and up. I mean, also in dimension 3. But so this is a little earlier, I think 60s or 70s, and this is maybe 80s. And these are both, Field's medals. Anyway, so this is really what the conjecture is. So I'm sorry that I got a little confused. But anyway, the theorem is that I kind of want to address a little bit. I mean, we have 5 minutes, so it's not a lot of time. But I can give you an idea, nevertheless, is that if X is homeomorphic, so if Xn is homotopy equivalent, so homotopy equivalent to Sn, then X is homeomorphic to Sn whenever n is greater than or equal to 5. And by the way, it's not usually true for diffeomorphic, because there are already examples of manifolds that are homeomorphic to Sn for n at least 7 that are not diffeomorphic. So if they're homeomorphic, then they definitely are homotopy equivalent. So it's not true in the diffeomorphism category. But anyway, so how do you prove this? So basically, you prove it like this. So if X is homotopy equivalent, then hold on, let me look at my notes. Then you do the following thing. So you take your X, and you remove 2 disks, or 2 balls. So you take your X, and you remove 2 balls. OK. You just choose 2 points, 2 separate points. You choose neighborhoods around them, and then you just remove 2 balls. And then you look at this guy. So this is your, say, Y. And then now, you can see the boundary of these 2 balls. You can see this guy, W. So now the boundary of W is 2 spheres. So you have kind of an Sn minus 1 A, this joint union with an Sn minus 1 B. And one of them has the opposite orientation, but kind of, it's a sphere that comes with the orientation that it comes with, but it's diffeomorphic to a sphere. So then, this W is a cobordism. That means it's a cobordism, as I explained, from one sphere to another one. And it's not hard to see, because it's homotopy equivalent to Sn, that pi 1 of W is equal to 0. And moreover, when you look at the inclusion of each of these spheres inside of W, these are also going to be homotopy equivalences. So when you look at the inclusion of this guy inside of W and this guy inside of W, these are also homotopy equivalences. I mean, I, of course, don't have enough tools to explain this properly. But just to give you an idea of how this goes. So, because of X being homotopy equivalent to Sn, you can find this cobordism, which is inside of X, which is a cobordism from one sphere to another sphere, in a way that the inclusion of the boundaries, of the 2 pieces of the boundaries, are homotopy equivalent. So that kind of means that, in a way, the cobordism is algebraic topology. It's very simple in the sense of algebraic topology. It's not seeing any invariance. And the theorem that Smale proved is that if this condition holds, then W is a trivial cobordism. So then W is a trivial cobordism. So it's a sphere times 0, 1. And this thing here is called the H-cobordism theorem. And basically, once you know this, then you're almost done. So actually, before saying that, let me just say how you prove the H-cobordism theorem. It's kind of like, of course I can't do that in 15 seconds, but I can just say, what do? You choose a Morse function here. So you have a Morse function that has a bunch of critical points. And then you apply the cancellation lemma that I explained last time and use it all the time. So basically, last time I said, if you have a Morse function, you have two critical points in this index difference 1 and a unique flow line from one to the other, then you can cancel them. And what you do here is you do something even stronger than that. So you start with your Morse function on the cobordism, and then you don't know really how these things connect, but there is a more complicated cancellation theorem, which is kind of when you have this intersection, but in homology, not just like directly. So you might have several flow lines, but when you look in homology, it's like in some kind of algebraic way, then you actually, most of them cancel out except for one. In sort of using intersection theory in some kind of way in homology. So if you can do that, then you can still cancel. So basically, you can prove that you can always cancel everything if you assume this condition of the two inclusions being homotopy equivalences, and pi 1 equals 0. So it's kind of a long story, and you might have to be able to cancel, you might have to create new critical points so that you cancel, and then you kind of keep going. And then with these conditions, you kind of can conclude that at the end, you find a Morse function with no critical points. So a Morse function with no critical points, if we have one boundary at the bottom and one boundary at the top, that has to be a product. No critical points, you have this diffeomorphism. Okay, so this is kind of a very short version of the H-cobordism theorem. But once you have this H-cobordism theorem, that means that your W is this. So what is X? So X will be this product. But then you have a ball on top, a Bn on top, and you have a Bn on the bottom. So basically what this is you can kind of shrink this cylinder to just a sphere. So basically what you have is you have a ball in the bottom and a ball on top. And that are glued along the sphere. So they're glued along a diffeomorphism. So that the conclusion is that your X is a Bn union Bn glued along a diffeomorphism of Sn minus 1. And then the last little lemma is that everything of this form is homeomorphic to a sphere. So this is basically, you can think of it as a Morse function with exactly two critical points, a minimum and a maximum. And every time you have this thing has to be homeomorphic to a sphere. And how do you prove that? Well, exercise. I guess I'm not going to write the formula, but I can just say how it is. You can just you have the northern hemisphere and the southern hemisphere. So what you do is you use the identity for one of them, and then you use phi to keep gluing. So you want to map from this to Sn, or from Sn to this. So you use the identity on the northern hemisphere, and then you use phi, this diffeomorphism on the southern hemisphere. And you just kind of use that for the sphere. As you kind of go, the hemisphere is just a product of 0, 1 by the sphere where you collapse the 0. So you use that this phi on all these guys, and then at the origin you just kind of take the south pole to the south pole, and this is going to be it's kind of easy to see it's a continuous invertible map, and the inverse is continuous, but the differentiability at the south pole is not true in general. That's why you don't get a diffeomorphism; you just get a homeomorphism. Okay. So I think that's the end. I'll stop here. So one more thing. So if you're an external student and you would like to take the test and get a grade, please let me know today. Send me an email right now. Okay? So se você é um aluno externo e você quer uma nota ABC, e você gostaria de fazer a prova remotamente, por favor, me manda um e-mail agora. Tá bom. Ok. Thank you.